Welcome back to ECE 320A. In this video, we want to actually derive the total complex power formula when we have a line voltage and a line current magnitude given to us, and then we might have the power factor, or we might have the impedance, which gives us then the angle of our impedance. And that angle, we could then take the cosine of that to get the power factor. Consistent with that is the total reactive power formula, which just needs the reactive factor, which is just the sine of that angle. Here are the two formulas that we will want to verify. And again, V sub L is not a phasor here. It's just the magnitude of the line voltage. And the line voltage doesn't matter how the load is connected. The line current, again, I sub L is just a magnitude, and it doesn't depend either on how the load is connected. The line current is always the line current, and that's the current in the transmission line of one of the phases. And we're assuming, again, a balanced three-phase system. Let's now derive these formulas for the total complex power. And by the total, I mean what are all three phases contributing in the total of the complex power. So we're assuming we want all three phases added up. And we want this total complex power to be expressed in terms of line voltage, line current, and power factor. And remember from a previous lecture, the line voltage is independent of the connection structure, and the line current is also independent of a Y or delta connection. But to derive these formulas from the techniques that we have available to us, we do need to fix one of the connections and then work with that and then derive these relationships. I'm going to go ahead and show this derivation using a Y connection structure. But you could do the same derivation. It's not going to be exactly the same, but you'll get exactly the same result or exactly the same expressions because those expressions do not depend on the configuration. They just are using the line voltage, the line current, and the power factor. Let's now look at a Wye connected load. And here is such a load. What I'm illustrating now, or what I'm using now, is I'm concentrating on one of these phases. If we can find the power, the complex power, or the real and reactive powers of one of these phases, since our system is balanced, we can just multiply it by 3 and end up with the total complex power. In order to find the power of a particular phase, all we need to do is take, here we have the A phase, so that means, let's take the phase voltage of the A phase, which we're now writing as some magnitude, V sub phi, at an angle of theta V sub A, and multiply that by the conjugate, complex conjugate of the phase current, which in this case is with the Y connection, I sub AA, and let's just assume that that has now a magnitude of I sub phi and an angle of theta I sub A. And we now want to know what's going to happen with the complex power in all three phases, so the total complex power. And if we want, we can, since we know the angle of the A phase voltage phasor and we know the angle of the A phase current phasor, the angle of the impedance of that A phase, and for that matter all of the phases, is theta sub v sub a minus theta sub I sub a. So let's look at the component powers, real and reactive. If we wanted to look at the real power per a single phase, and here we're just focusing on the A phase, that would be power of the phase is now for the real power, that's now the magnitude of the voltage times the magnitude of the current times the cosine of the angle of the impedance phasor, or the cosine of the difference between the voltage phasor and the current phasor. Now, if we wanted to write this in terms of line values, we could do that. What's the magnitude of the line voltage in a Y configuration? Now the line voltage would be this particular voltage. And we only need the magnitude. And how is that line voltage related to the magnitude of the phase voltage in a Y configuration? It's now a factor of the square root of 3 bigger. So now we have in our formula the phase voltage. If we wanted to rewrite that in terms of the line voltage magnitude, we would say, oh, V sub phi is actually the square root of 3 less than V sub load. So this is now just another way of writing V sub phi. What's the line current in terms of the phase current in this Y configuration? Well, the phase current is simply the current going through that A phase impedance, but that's the same as the line current I sub AA. So this I sub phi in this case is just the same as I sub L. And the cosine of theta sub phi doesn't change. This is now just our power factor. So what have we found? We now see that we have 1 over the square root of 3 magnitude of the line voltage times the magnitude of the line current times the cosine of theta sub phi. That's for one phase. If we wanted the total real power, then we multiply that by 3. The total real power is now 3 times P sub phi, but 3 divided by the square root of 3 is just the square root of 3, since 3 is the square root of 3 times the square root of 3, and we take one of those square root of 3's away when we divide by it. So the total real power is now the square root of 3, the magnitude of the line voltage, times the magnitude of the line current, cosine of theta sub phi, or times the power factor. And I think you can see that the reactive power per phi is going to be the same. Q sub phi is now the magnitude of the phase voltage times the magnitude of the phase current sine of theta sub phi. Or written in terms of line variables, V sub phi in this Y configured load is now V sub L over the square root of 3, I sub L sine theta sub phi. And we can end up then with a similar looking expression for the total reactive power. Q sub t is now 3 Q sub phi, which is now the square root of 3, V line, I line, sine theta sub phi, or times the reactive factor, which if we wanted to find the total complex power in terms of line voltage and line current, we now have the total complex power, S sub t, is now P sub t plus in the orthogonal direction Q sub t, or P sub t plus J Q sub t. This is now square root of 3 V line, I line at an angle of theta sub phi. Meaning now we're just using Euler, or we converted back to polar form if we go the other way and simply rewrite this in rectangular form. We now have V line, I line times cosine theta sub phi plus J sine theta sub phi, and that's the total complex power. And that's the formula. Those are the formulas that we had just derived. The total the total real power is the square root of 3 V line, I line cosine theta sub phi, or the square root of 3 V line, I line power factor of the load. Q sub t is now square root of 3 V line, I line sine theta sub phi, or the square root of 3 V line, I line reactive factor of the load. That now gives us a way, if somebody now tells us the total real power or the total reactive power, and we know we can maybe measure the line voltage and the line current, and somebody tells us the power factor or doesn't, we can interrelate those quantities. If we're given 3 of those 4, we can solve for the 4th. And that's what you'll want to do in some of the problems, and in particular a quiz that follows this lecture.